Here's a question that feels almost too obvious to bother asking, right up until you actually try to answer it. Why did ancient humans start cooking their food? Every other creature on this planet eats exactly what it finds. Wolves don't marinate a kill. Bears don't roast the fish they pull from a river. Not one dolphin has ever assembled anything you could fairly call a meal. And yet every human culture ever documented, without exception, on every continent, in every climate, at every level of technological development, cooks its food before eating it. Think about what that actually means. It is the one truly universal human behavior, not language, which varies wildly from one group to the next, not tool use, which plenty of other species also manage in some form, not art, religion, or trade. Cooking, heat, deliberately applied to food before it ever reaches your mouth. Only humans do this, and every human population that has ever existed has done it. And here's the part that should genuinely stop you. We've been doing this so long that our bodies have quietly become dependent on it, the way no other species depends on a piece of technology it uses. That dependency is the detail almost nobody stops to think about. You don't cook mostly because it tastes better, although it does, dramatically. You cook because, in a testable sense, you cannot survive without doing it. Your body has been physically rebuilt over an enormous stretch of evolutionary time into a shape that assumes cooked food is already on its way. Your jaw generates a fraction of the force a chimpanzee's jaw can produce. Your gut runs shorter. Your teeth are smaller, your enamel thinner, your whole digestive blueprint different from our closest primate relatives, all of it pointing toward the same conclusion. A body engineered around food that fire has already gotten to first. None of that is a design flaw. It's a record, physical proof that some ancestor made one of the most consequential decisions in the history of life on this planet, and then had their descendants' bodies quietly reorganized around it, generation after generation, for roughly the next million years. And here's where it gets stranger. We don't actually know how it started. Intentional or a complete accident. Maybe a scorched root pulled from the ashes of a wildfire, tasting better than the raw version, or something worked out more slowly through repeated trial. We aren't even sure whether the first deliberately cooked meal was plant or animal. What we do know is that at some point, one individual tasted heated food, recognized it as something better, and the trajectory of an entire species shifted permanently from that moment forward. Let's rewind to what things looked like before any of this, because the before is what makes the after land so hard. Roughly 2 million years ago, our lineage sat at something close to a fork in the road. Australopithecus, upright, increasingly clever, spread across the African savanna, was still running essentially the same dietary program a modern chimpanzee runs today. Raw fruit, whenever it could be found. Raw roots, tough and stringy. Raw bark, raw shoots, the occasional insect or small opportunistic kill. That diet demanded an almost unbelievable amount of chewing. A wild chimpanzee spends close to half of every waking hour doing nothing but processing food in its mouth. Not hunting, not resting, not anything resembling complex social behavior. Just grinding fibrous plant matter down, mouthful after mouthful, because raw food gives up its calories grudgingly, with no shortcut around the mechanical labor required to reach them. Harvard primatologist Richard Wrangham didn't just theorize about this from a comfortable distance. He traveled to Uganda and ate what wild chimpanzees eat for extended stretches to understand it firsthand. His own account was almost comically restrained. Tough, bitter, exhausting to get through. And after long, steady chewing on a single piece of wild fruit, almost nothing worthwhile to show for it. That left him with a conviction that reshaped his entire research question. A human body, with our comparatively weak jaw and short gut, simply could not survive long-term on that raw ancestral diet. Wouldn't enjoy it. Could not physically extract enough usable energy from it to keep a functioning human alive over time. Which raised an obvious problem. If our bodies can't run on what our ancestors ate 2 million years ago, something changed between then and now. Something delivered far more usable energy per mouthful. Something freed our ancestors from spending half their lives with their jaws working. Something drove the exact anatomical shift visible in the fossil record, separating our genus from everything before it. What was that something? Wrangham's answer, reached while staring into his own fireplace in Massachusetts in 1997, was cooking. Not the shift toward eating more meat, proposed by others as the pivotal turn. Not bigger brains that then figured out cleverer foraging strategies. Cooking. Fire. Applied to food before a single bite. He published the formal hypothesis in 1999 in the journal Current Anthropology, later expanding it into a widely read book, His argument wasn't that cooking was a pleasant bonus that arrived once humans got smart enough to invent it. Cooking was the engine itself. We didn't evolve large brains and then stumble onto cooking. We started cooking, probably by accident, and our brains grew as a direct consequence. The cause and effect run backward from what most people assume. Now, here's the part that should genuinely stop you. To understand why, you need to look at what heat actually does to food, because the transformation goes far deeper than most people ever consider, and the evolutionary logic is hiding in those exact chemical details. Take a starchy food, a yam, a root, a grain, raw. Its starch sits packed into dense, tightly wound granules that digestive enzymes can barely get a grip on. Apply heat, and those granules absorb water and swell open, a process called gelatinization. What was locked becomes accessible. Same object, same weight, dramatically more energy extracted, purely because heat got there first. Protein undergoes something just as dramatic. Raw meat is bound by tough structural fibers, collagen among them, that resist even strong stomach acid. Heat denatures those fibers. Unraveling their structure into simpler strands, your enzymes can tear through far more easily. Heat does something else worth pausing on. It neutralizes many of the natural toxins and disease-causing organisms sitting inside raw food, compounds that plants and animal tissue carry specifically to make themselves harder or more dangerous to eat. Applying heat destroys a meaningful share of that defensive chemistry, opening up food sources that were genuinely risky in their raw state. There's a fourth transformation worth naming, one that gets far less attention than it deserves. When heat meets the proteins and natural sugars on a food's surface, it triggers a browning reaction chemists call the Maillard reaction, the exact process behind seared meat, toasted crust, and roasted vegetables tasting like an entirely different substance from their raw or boiled equivalents. That reaction generates brand new compounds that weren't present in the raw ingredient at all, some of which your gut absorbs with far less effort than the originals. Stack gelatinization, denaturation, detoxification, and the Maillard reaction together, and cooking stops looking like a matter of taste and starts looking like outsourced digestion. Fire does a genuine share of the chemical labor before food reaches your mouth, so your gut spends far less energy finishing the job. Comparisons of identical meals, cooked against raw, consistently find meaningfully more extractable energy in the cooked version, the entire gap between thriving and barely scraping by, when calories are scarce. And then there's the time. Think carefully about this part, because it's easy to skim past. Wrangham estimates pre-cooking hominids spent something close to half their waking hours simply chewing. Once cooked food became routine, that number collapsed toward roughly the single hour modern humans typically spend eating in a day, 4 or 5 extra usable hours every single day, freed from the mechanical necessity of grinding down enough raw material just to stay alive. Repeated across hundreds of thousands of years, consider what your ancestors could do with that reclaimed time. Hunt with more coordination, build better tools, maintain relationships within and between groups instead of spending every waking moment alone with a mouthful of fiber. Teach the next generation. Sleep longer and sleep more safely, since fire kept nighttime predators at a distance, letting a group rest together on open ground rather than scattered defensively in trees. Explore further. Plan ahead instead of living meal to meal. The campfire wasn't just a cooking device. It was a security perimeter against predators, a source of warmth stretching the range of livable habitats, a gathering point that made sustained group contact possible, and a time-generating technology whose benefits compounded across every generation that inherited it. Now here's the part that should genuinely stop you cold. What actually happened to the human body, physically, right around the period cooking is believed to have started? Somewhere around 1.8 million years ago, something fairly abrupt shows up in the fossil layers. Homo erectus appears, and compared to what came before, the differences are stark. A noticeably larger brain relative to body size, a taller frame, longer legs, built for sustained movement, and, critically, a smaller jaw, smaller teeth, and a meaningfully shorter gut. That gut change may be the single most striking anatomical shift in our entire fossil record. In chimpanzees and most other primates, the digestive tract is enormous relative to body size, built around a large stomach and colon dedicated to slowly fermenting huge volumes of tough, low-calorie plant material, a costly system demanding a constant heavy blood supply and large volumes of food just to keep itself operating. In Homo erectus, that expensive apparatus shrinks. There's really only one way a species can afford that. Incoming food has to require far less processing for the same energy. In most primates, gut outweighs brain by a wide margin. In modern humans, that relationship flips entirely. Our brain now outweighs our gut. Less gut, more brain. A metabolic budget being reallocated, and the timing lines up closely with the shift toward cooked food. Here's why that reallocation matters. Your brain, sitting quietly in your skull right now, consumes close to 20% of your entire body's energy budget just idling. Gram for gram, costing roughly 9 times more to run than an equivalent unit of muscle. By far the most metabolically expensive tissue you own, and it cannot be maintained without a calorie-dense diet feeding it. Brazilian neuroscientist Susana Herculano Huzel ran the numbers on what that would cost a raw food primate. For a gorilla to grow a human-sized brain on its current raw diet, it would need roughly 2 extra hours of feeding stacked on the 8 or 9 it already spends daily, pushing total feeding time past 10 hours, leaving almost no time for anything else. The math doesn't work for a large-brained animal stuck eating raw food. There's experimental proof of this beyond fossils. In a study run by researchers alongside Wrangham, mice fed cooked meat gained noticeably more weight over time than mice fed the identical quantity of raw meat. Every other variable held constant. The one difference was whether heat had touched the food first, about as close to a direct demonstration as you'll get of a pattern the fossil record only shows indirectly. A fair account includes where researchers disagree. The expensive tissue hypothesis argues the critical shift wasn't specifically cooked starches, but a broader move toward calorie-dense food generally, including raw meat and marrow. The social brain hypothesis proposes brain size tracks social group complexity more closely than diet. Neither theory has decisively won. Most researchers suspect all three forces reinforced each other. The archaeological dating adds a genuine layer of uncertainty. If cooking became essential around 1.8 million years ago, direct evidence of controlled fire doesn't show up clearly until much later. Deeply buried ash and burned bone in a cave in South Africa date to roughly 1 million years ago. A cave in Israel called Kesem Cave shows something more compelling. A hearth in the same spot, reused somewhere between 300,000 and 400,000 years ago, alongside cut-marked, heat-treated bone, suggesting a dedicated cooking spot rather than occasional fire use. Widespread hearths across many sites don't become common until roughly 400,000 years ago. Some archaeologists find that gap troubling. If cooking had been constant for well over 1 million years, we'd expect earlier, more abundant evidence. Others respond that small, open-air fires simply don't survive geological timescales, and the missing record reflects preservation limits, not absent behavior. That disagreement remains unresolved. What isn't up for debate is what happens to a human body denied cooked food entirely. And this is where the deep past becomes something you can verify today. Long-term studies of people on a strictly raw, unheated diet consistently show progressive, unavoidable weight loss because the body burns more energy processing raw food than it recovers from it. Close to half of women on a strict raw diet over an extended period stop menstruating altogether, a direct signal the body has judged its energy supply too unreliable for reproduction and shuts that function down first. A diet that halts reproduction in roughly half the population, attempting it isn't a lifestyle inconvenience. It's a diet that leads straight toward extinction, inside a single generation. One more layer explains why cooking reshaped more than biology alone. A fire that must be built, tended, and defended forces people to gather, share what it produces, and cooperate to protect it. An arrangement that rewards partnership, someone tending the fire while another forages, holds a real advantage over anyone surviving entirely alone. Some researchers argue this is where a division of labor between partners first took shape, along with the pair bonding built around it. Not romance, but a working arrangement anchored to a shared hearth. Consider what happens once people gather around a fire in the evening. Bellies full, predators kept at a distance, hours of non-chewing time available before sleep. Storytelling becomes possible. Passing down which berries were poisonous, which valley had water, becomes possible. Laughter, teaching, all of it fits into exactly the hours once swallowed whole by chewing. The fire didn't just feed the brain. It created the conditions for that brain to start doing the things that made us recognizably human. So, the next time you're at the sink at some inconvenient hour, scrubbing burnt rice off the bottom of a pot, take 1 second to register the weight of what you were just doing at that stove. You were carrying out the oldest, most distinctly human technology in the entire span of our species' existence. Older than farming by roughly 1 million years. Older than any written language. Older, quite possibly, than language itself. You were repeating something an ancestor of yours was doing around a modest fire on the African savanna more than 1 million years ago, an act that rerouted the trajectory of our lineage. It shrank your jaw. It shortened your gut. It freed your time and protected your nights. It organized your earliest social world and freed enough biological energy to build the very brain you're using right now to follow this sentence. Every meal you cook is a continuation of the exact act that made you human in the first place. even at midnight, even scrubbing a pot you should have soaked an hour ago. The principle still holds.